This lesson is about displacement time graphs. A displacement time graph is a graph in which displacement is plotted on the y-axis and time on the x-axis. We are going to introduce ourselves by discussing two terms, that is distance and displacement. Distance refers to the length between any 2 points, say A and B. For example, the distance between any 2 given towns. Distance is a scalar quantity. A scalar quantity is a quantity that has magnitude or size only. So here we are not concerned about the direction, but the size. How big, how long, how far. The unit of distance is meters, which can be written using the simple small letter m. On the other side, displacement refers to the length between any 2 points, say A and B, in a specified direction. Therefore, we are concerned about the magnitude and direction. That's why we say displacement is a vector quantity. A vector quantity is a quantity that has both magnitude or size and direction. If 2 towns were to be connected using a straight line and we measure the length between those 2 points, then that's what we call displacement. The SI unit of displacement is meters, which is the same as the SI unit of distance. Sometimes distance and displacement can be used interchangeably, or one can be used in place of the other. So displacement time graphs can also be referred to as distance time graphs or position time graphs. Examples of displacement time graphs. Our first example, we have displacement on the y-axis and time on the x-axis, then a straight line. We can see that this straight line is parallel to the x-axis or the time axis. So what important information can we draw from this kind of a graph? One, we can see that this body is not moving because there is no change in displacement. Therefore, the body is at rest after covering some displacement. So we are saying after covering some displacement because we can see this line is above 0, meaning that there is some distance that has been covered, but now as time moves on, there is no change in displacement, meaning that the body is not moving or it is at rest. The second thing that we can say is that if the body is not moving, then its velocity is 0. Let's move on to our second graph. We have displacement on the y-axis, time on the x-axis, and then this straight line. Now this straight line is sloping from bottom left to top right. So one thing that we can say is that displacement increases uniformly with time. So this is a constant velocity. And when we talk about constant velocity, we can also say that acceleration is 0 because there is no change in velocity. Another example, that is our third example, displacement again on the y-axis, time on the x-axis, and then a straight line. This straight line slopes from top left to bottom right. And one thing that we can say is that displacement decreases uniformly with time, as we can see. As time increases, displacement decreases. So this gives us a negative constant velocity. Negative constant velocity shows us that this object is in its return journey. It had already traveled some displacement up to this point. Now it is going in the reverse direction, or going backwards. So acceleration is 0, since we are saying that the velocity is constant, though it's negative. Our fourth graph, this is the graph. We can see that this is a smooth curve, and what we can deduce from this smooth curve is that the displacement increases non-uniformly with time. We are saying it's non-uniform because it's a curve, it's not a straight line. Then it shows a non-constant velocity. This non-constant velocity is actually a velocity that is increasing with time. So when velocity is increasing with time, we say that the object is accelerating. On to our fifth graph. Again, a graph whereby time is on the x-axis and displacement on the y-axis. Then we're getting a smooth curve, and from this graph we can see that displacement is increasing non-uniformly with time. This shows non-constant velocity that is changing, and this change is actually a decrease. So we say velocity decreases with time. When velocity decreases with time, it tells us that the object is decelerating. Now let us discuss how to determine velocity from a displacement time graph. We're going to discuss this by use of an example, and this is the example we have: a displacement time graph. So we have the axis, then the scale, a straight line. So how do we get velocity from this graph? Anytime we want to get velocity from a displacement time graph, we simply determine the gradient. So velocity equals to the gradient of a displacement time graph. Gradient is given by the rise over the run, or change in the y-axis over the change in x-axis. So let us determine the rise. The rise, or the change in y-axis, is from 0 to 20. So 20 minus 0 gives us 20. What about the run? The run is actually the change in the x-axis, which is from 0 to 5. So 5 minus 0 gives us 5. So the rise is 20 and the run is 5. Let us substitute in our expression. So this is equal to 20 over 5. 20 divided by 5 is equal to 4. Since we are getting velocity, then the unit is meters per second, and that is our answer. The steeper the line, the higher the velocity. For example, having this graph, displacement time graph, and this graph of one of the objects, call it object A, and another graph of object B, we can say that object A has a higher velocity than object B. So if you compare between the two, object A is the one that is faster than object B. Let us now discuss another question. We are required to study the diagram below and answer the questions that follow. Our diagram is a displacement time graph. We provide scale on both axes. Then the graph shows the motion of a particle between stages A, B, C, and D. Questions. First question, what is the initial displacement? To get the initial displacement, we consider the displacement at the time where the particle was beginning its journey, and that is at 0 seconds. That displacement is actually 0 as well. So initial displacement is equal to 0 meters. Second question, state the maximum displacement reached by the particle. Maximum displacement is going to be read on the y-axis, the highest point of the graph on the y-axis, and that is this point, which is 80 meters. So maximum displacement equals to 80 meters. Question 3. Calculate the velocity in the first 20 seconds. We need to first identify the first 20 seconds. Then we say that velocity equals to the gradient, but gradient equals to the rise over the run, or change in y over the change in x. So the first 20 seconds is from point A to point B. So that is this region here. So what is the change in y-axis? Change in y-axis is the maximum point along the y-axis minus the minimum point, that is 80 minus 0, which is 80. Then the change in x-axis, or the run, is from 0 to 20. So 20 minus 0 is 20. Therefore, we substitute the values for the rise and the run as 80 divided by 20. 80 divided by 20 is simply 4, and this 4 is meters per second. So that becomes our velocity for the first 20 seconds, or between point A and B. The next question is question 4. Explain what is happening between point A and B. Let us identify point A. This is point A and this is point B. So we can see that between point A and B, displacement increases with time, but the increment is uniform since this is a straight line. So clearly we can see that displacement increases uniformly with time until 80 meters. So this shows that the object is moving at a constant velocity for 80 meters, or from 0 until 80 meters. Question 5. Calculate the velocity in the last 20 seconds. Velocity is given by the gradient, and gradient is given by the rise over the run, or change in y-axis over the change in x-axis. So how do we get the rise and how do we get the run? The rise is given by taking the difference between point C and D in terms of displacement. So, for us to get this, we take the displacement at point D, which is 0, minus 80 meters. So 0 minus 80 gives us negative 80. Then the run is taken to be 70 minus 50, which is 20. So let us now substitute negative 80 for the rise and 20 for the run. So negative 80 divided by 20, it gives us negative 4. This negative 4 is supposed to be our velocity, showing that the body is moving backwards. That negative only indicates the direction, which is backwards, and the unit is supposed to be meters per second. Now try out the following two questions. Question 1. Study the diagram below and answer the questions that follow. This is the diagram. Question A. Which object or objects is moving at a constant velocity? B. Which object or objects is moving backwards? C. Which object or objects is accelerating? D. Which object or objects is at rest? Then second question, velocity is obtained from a displacement time graph by determining the gradient. Is it true or false? Select the correct one. Thank you, and I hope to meet you in the next lesson. Goodbye.